Okay, welcome guys. So in this video, let's keep talking about linear algebra. So basically, we already talked about the vector space and also basis. And the previous video, we talked about some interesting thing called the dual space. Okay, so in this video, let's talk about inner product space. Okay, so this is I should say the most important part, linear algebra. But so after this, I think we can finish the first part of the linear algebra. Okay, so yeah, let's quickly see. Yeah, so I start still setting the vector space over field F has an inner product. So it's a definition. So has an inner product. It's an inner product. Okay, so I should say it's an inner product space. So basically, if you have if for any two vectors, let's say UV and UV in V, and we got element which is U dot U. I use parentheses U comma V, which is a field F satisfied. Okay, so satisfied. The first one is the UV equals to VU conjugate. Okay, so since in this video, since I need to use the definition of conjugate, right? So actually, I only assume that the field is basically a complex number. Okay, and also U greater or equal to 0. Greater or equal to 0 should also view as a complex number. Okay, so and so also if U is 0, if and only if U is 0, so the only inner product can give 0 must be the 0 vector. Okay, which is also this. If you get so if you get alpha, let's see, you get alpha U beta V, W is the same as alpha U W beta V W. Okay, so basically these are all for all U V and also for all alpha beta. Okay, so you can get some, yeah. Also, so from this you can easily show that if you times the constant on the right element, let's say you get U alpha V. From the first one, you can change it into alpha V U bar, and then for the third one, you can change it alpha bar V U bar, and you change it back, you get alpha bar U V. So if you times any element on the right one, then you should get a complex conjugate. Okay. Okay, so example. So the first example should in a usual field field in N, or basically complex N, the standard inner product. So standard. So there's a standard inner product. Basically, it's from your high school that you get alpha 1, alpha 2, alpha N, beta 1, beta 2, beta N, and your inner product can define to be alpha 1 beta bar, alpha 2 beta 2 bar, alpha N beta N bar. So this is U, this is V, this is UV. Okay. Okay, and let's see now example. Basically, if you talk about all the continuous complex function, so basically all the V is basically all the continuous function defined on the 0, 1 map to a complex number, and you can define inner products for ft and the g of t, defined to be 0, 1 ft g of t dt. Take the bar here. Okay, exercise for you to check. This is the inner product. Oh, by the way, so the difficult one is to show that if it's 0, then f is identity 0, right? So you should prove that if 0, 1 f squared dx is 0, or absolute value squared 0, then you should prove f of x is 0, right? So in this part, you need to use some advanced calculus, so real analysis. You need to prove by contradiction. Suppose you get some point which is non-zero, and you choose a very small interval, and you can prove its contradiction. Yeah, but you should check by yourself. This is it. Okay, so once you have inner products, then I can define a length. Right? This is very simple. So the length is just written as BB. Basically, the absolute B defined to be what BB, right? Take a square root. By definition, BB is greater than or equal to 0, so we can take a square root. This is the length. Okay. And you can also, so by definition, you can show that the alpha U is basically our absolute value U. Okay, so this is basically trivial, so prove by yourself. Okay, and let's talk about theorem. Basically, it's the Cauchy-Schwarz. So this I already make a lot of videos prove this. Also the Cauchy inequality. So basically, the UV inner products at some complex number. If you take the modulo or less or equal to the U norm, has to be norm. Okay. Yeah, so this is there are other proofs. So yeah, but let me still quickly give the proof. So if one of is 0, so if one of UV is 0, then we are done, right? We got both and left and right 0. Okay, so okay, so let's see. So suppose let's do some simple case. Suppose UV is a real number, the inner product UV is real, and the U is non-zero. Then I can easily show that right. So for each lambda, so lambda U plus V, lambda U plus V. For any lambda, you pick any lambda belongs to a real number. Then you can calculate by definition it should be greater or equal to 0. So you get lambda square UU plus 2 lambda UV plus V squared. BV, right? So this is basically lambda square U squared and 2 lambda UV plus V squared, right? So by definition, this is the quadratic form of lambda, right? So and it must greater or equal to 0. So determinant basically is 4 UV squared minus 4 U squared and V squared should less or equal to 0. So which prove that the UV absolute UV squared. So now it's a real number, right? So it has this property. Okay, so let's see. So how about case? How about a case when UV is complex? So basically, it's not real. Okay, so in this case, let's say alpha is UV, and this complex not real, so definitely not 0, right? So I can let you alpha V, or alpha UV, right? So alpha is divided by UV, right? So this is just 1. Okay, so these guys real, right? These guys real. So we can replace. So we can use the Cauchy-Schwarz for real parts, for the real version. So I get the 1 equals to the inner product V, and should also equal to the norm of U and the norm of the V. Okay, so simple, easy to show that. So remove this alpha, and you get it. Let's see. Right, since it's known, right, you need to take the square root, so it should be this. Let's see. Sorry, there's no square. So this is the inner product of UV. So I think this is the same as, yeah, it's this one, right? Yeah, so we've only proved the real part, and then for the complex part, we do the Sadytovich shape. Okay, so next we talk about orthogonal. Okay, so definition. So if UV belongs to V, so we say that V is orthogonal to U, means that UV is inner product 0. Okay, simple definition. So definition, we can talk about the space, the orthogonal space. So given the subspace of V, right, one can construct a W. So how should I say this in words? So actually, the orthogonal space of W basically is all the vectors belongs to V, such that VW0 for all W belongs to W. Okay. So your exercise is W. This is orthogonal space is also a subspace. Okay, so let me quickly let me just quickly check for you. So you need to prove that if let's say W1, W2 in the orthogonal space, the addition is, so it's very easy, right? Because if they are in a space, then I use B1, B2, right? Otherwise it's a little bit confusing. So you can check that. So now B1 plus B2 for W, just B1 W plus B2 W, right? But this is 0, right? This is 0, so 0 plus 0. By definition, since B1 and B2 in the product space, in the orthogonal space, 0, so we show that B1, B2 also in the W space. That W also okay, and then you times the constant, it's trivial, right? Times constant. I see 0. Okay, so also easy, so easy already show that it's right. So this is W complement. Oh yeah. So okay, so let me just reading. So whenever I say this, I like to say W complement. Okay, so my word is so I pronounce it as W complement, means that this space for a given inner product. Okay. Okay, and moreover what? W and the intersection of W complement is 0. Okay, why is this? Okay, so let's see, you pick some vector y in the list W. So y should be, so y in W, right? And but y in the W complement means that y is what? Y is also going to itself, right? So which the y is 0. So this is the inner product rule, right? Because y in W complement means that the W complement should also go to each other. So y should also go to itself. So y must be 0. Okay. The definition. So the set of vectors vi v is also normal. It's called also normal. If basically if vi and vj or any two inner vector products will be delta I. So let me just write down, so 1 I the same j, else just 0. So only so basically it's also normal, right? So each two vectors, if they are the same, the product is 1, the inner product is 1, else is 0. With the theorem, so given a vi from 1 to n is also normal set, and it's linear independent. Okay, so quick proof. So how should I prove? So suppose that I get beta I vi 0 from 1 to n, then I just do the inner product of vj. So I get beta I delta ij is 0. Right, but the list is just only the j equals to I survive, so I get beta j. Right, but this argument is basically for every j, right? So for every j, beta j is 0. So that means if you have this equation, then you finally arrive at all coefficients 0. So they are linear independent. Okay. Yeah. Okay, and also you get a simple lemma. So this lemma says that if you have a also normal set I from 1 to n, and then you get a vector W belongs to V, and then you can take U defined to be W minus W V1 V minus W inner product V2 minus W V3 and up to minus W Vn Vn. Okay, and your exercise is to check that U is also normal to V. So U be J0 or J from 1 to object. Okay, so this is trivial exercise. We just dot with Bj. Okay, so basically one can say that U belongs to the span of this Vi I from 1 to n, and take the complement, right? Yeah. Okay. Yeah, so this is basically the famous grand schematic also normalization process. Sure by yourself. Okay. Theorem. If V is a finite dimensional in a product space, then V has an also normal set as space. Okay, so generally, maybe some people will think that this is trivial, right? Because one can define this, and you can say that you choose bases at 1, 0, 0, 0, or 0, 1, 0, 0, 0 as your basis, right? Basically, by definition, it should be also normal, right? But the problem is that I didn't give you the what's the definition of inner product in this case. So in general, this theorem is non-trivial, since that what I'm saying is that all the inner products on V. I'm not just focused on a standard one. I mean, if I focus on standard one, a standard basis will directly also normal. Okay, so non-trivial part for this theorem is this works for any inner product space, not just for the standard one. Okay, so the proof is just basically the lemma. So using a previous lemma, I mean, you can, so first you get some vector, right? W1, W2, Wn is the basis of V. So you pick out a vector, you pick out the basis, and then you first normalize the first one, that V1 to be a normalization. And then you define a V2, right? You can define a V2 by this previous process. So you get you use your roughly W2 minus minus 1. You use this one and then minus the W2 V1, right? And do the normalization. Right, and once you do that, you can define V3 to be W3 minus W3. Yeah, so if you need to do a normalization. So W3 V1 and W3 V2, and then you do the normalization. So you do the normalization, and you keep going. Okay, and obviously that by construction, this is correct. Okay, yeah, so we basically prove these results. Just basically use the grand schematic also on normalization process. Yeah, so I should talk about examples, but I don't want to. Okay. So yeah, so let's still talk about theorem. Okay, so theorem is that if V is a finite dimensional vector space, and you take W subspace, right? And your direct sum is also, sorry, not direct sum, but the complement is also a subspace. We already proved. So I will show that V is just W direct sum W complement. Okay, so the very good thing is that the W intersection with W complement is already proved to be 0, right? So yeah, so we just need to prove that every vector V can be written as a W in this, and also some W maybe star, and their sum will be V. Okay. So the proof. So there are many proofs, but I want to use the simple way. So I can choose a basis, right? Choose the basis of this, let's say W1, W2, up to Wn. Okay, and I can define a V to be V minus, sorry, W star to be V minus VW1. So this W1 up to Wn is also normal, right? So I can choose also normal basis in W1, VW2, W2, minus VWN, Wn. Okay, so by construction, we already proved this W star will also go on to any vector in W, right? So W star will be W complement, and by your definition, so this guy also is W, right? Because W is spent by this. So V is basically this guy plus W star. Okay, so proof is done. Yeah, almost trivial. Okay, so I think this is just inner product space. So inner product space is not difficult. Next time we talk about modules.